will be on exercise sheet 5. And you will see that Silo theorems are very important for the classification of groups. That means if one wants to ask you how many non-isomorphic groups are there of order p square, p cube, p square q, and so on, some particular cases, because we still have we have not sufficient group theory to analyze everything. So whatever small orders we can do it, that is in the exercise sheet 5. And also now I will start mixing up with the linear algebra. And as I told you earlier, my aim will be to give simple group. These projective groups are special, projective linear groups are simple. But I will need little bit about projective spaces, and just now I heard Nitin doing some projective planes and so on. So how many of you have exposition to projective spaces, or should I do it?
Exactly do you want in what all do you want in projective spaces?
Sorry, who is talking?
Sir, you asked.
Ishan.
Hello? Yes, sir.
What is your question?
You asked whether we have exposure to projective spaces, right? So
Yes.
What all topics are you asking for? I can talk about, I have seen RP and CP and homogeneous coordinates, and I've done a bit of things along those lines, but what exactly are you asking for?
I am asking for, do you know what a projective space over a field? Projective
No.
space over a field in general, or arbitrary
just
field.
Over R and C.
Yeah, but what is so special about R and C? Over a field, and especially I will need it for over a finite field. So I will briefly recall it, and construction is same as that of real numbers and complex numbers, but it will be, because it is a finite group in that, if field is finite, then the projective spaces are also finite. It's like affine spaces. Have you become comfortable with the affine spaces that we have been doing in the last few lectures? Hello, Ishan. Are you still there?
Yes, I am. Yes, sir. Your voice was getting cut. I heard affine spaces, but I did not hear anymore.
No, in so many assignments are there, no?
Yes. No, I'm saying your voice got cut. I couldn't hear what you were saying.
Affine spaces, affine maps, and so on, that we have in assignment sheet 2 and supplement. If that material is
yes.
That one, if it is that will be helpful. Anyway, so let me start now. I want to already a little bit late. So what do I want to do now? I want to first give example. One more remark I wanted to make. And you see this assignment 5 will have, I have it here, I will show you. Assignment 5 or 4, 5 will have the summary. So actually these proofs I have written down. What I have not written down is this other proof which I gave. And there are couple of remarks here which I have not done in the class, but they are simple enough, you can just read it. These are lecture notes. This violet color is a lecture summary of results. So it's for your handy reference if you are doing these problems. All right, so I just want to discuss one proposition which will be helpful to give. So ultimately we want to classify which are the simple groups. That is a big project, but I will not classify, but I will give only a few more examples. All right, so this is the proposition I want to note, and then we will go to so G, let G be a non-abelian group. non-abelian group of order p power alpha m with alpha is equal to Vp of n and p and m are co-prime. P doesn't divide m. This is my n. Then I want to prove that, and I assume, suppose that p power alpha does not divide m minus 1 factorial. Then I want to prove that then G cannot be simple. Simple means that is no non-trivial normal subgroup. That is, no, there is. There exists normal subgroup which is proper and which is not trivial normal subgroup. That is what we want to prove. So, proof. I will use the silo theory. This is a typical example how silo theory is used to decide the group is simple or not. But it cannot be done to every order group, but some such assumptions. And you see, these assumptions will come from some standard group actions. All right. So let P be a silo subgroup. P silo subgroup. That we know it exists by Salo theorem 1. So the cardinality of P equal to P power alpha. And then we know whenever you have a subgroup, that group operates on the left cosets. That is so very important. So G operates on G by P. And what is the action homomorphism? This operation is obviously by the left multiplication. Then I will say with action homomorphism. That is action homomorphism is from G to symmetric group on G by P. So this is I denote by theta if you remember, and G going to theta G. This theta G maps the coset here XP to GX. This action is so very important. We have used it so many times that it should fit in your head every time without any this one. And I am hoping that we will want to check what happens to the kernel. I know this kernel is a normal subgroup. I want to check if it is proper. First, I will check it is non-trivial and it cannot be the whole group G. That is what we will check. And then we are done. All right. So what is the order of this group? This is a group homomorphism. This theta is a group homomorphism. And the order of this group is what? This group has order G mod P has cardinality m.
So m factorial.
M factorial, very good. Cardinality of this group equal to m factorial. Okay, so suppose kernel is trivial. If kernel of theta it is trivial, then the G will be a subgroup here. G, this theta map is injective and therefore G will be subgroup. Therefore, order of G will divide the order of this group. So we will get then P power alpha m, which is the order of G. This will divide order of SG by P, which is m factorial, and therefore I will cancel B m, and that will imply P power alpha will divide m minus 1 factorial. Contradiction. This is not possible. Therefore, this cannot be normal. Not possible by assumption. So therefore, we check that. Therefore, kernel of theta is non-trivial. And can it be identity? Can it be, what is your, can the kernel be whole? Or is it a proper subgroup? Is it G? Can kernel be G?
Sir, it is.
Hello?
No, sir.
Why?
Sir, it is CELO subgroup.
So
action is not trivial.
Kernel is not a CELO subgroup, is it?
P is not P is not equals to G.
Fine. So what? Kernel of theta cannot be G. That you have to justify. I will write you a check. Of course, P is a CELO subgroup. That's okay. Please check this. So this is also not very simple, very easy. But you see here, you have to say something on the assumption. All right, so I will go on. So that is what a typical application of Silo theorems. All right, now I will switch on to the groups, the matrix groups. And for that, I will assume that you know basic linear algebra. All right, so let me start very simple. I will recall the statements today in the format that I want to use it. And maybe you are familiar, maybe you are not familiar, but you will know, I'm sure you will know these results in some format. All right. So this is what I want to recall now, elementary matrices first. And my intention is always to use a geometric language which we got it from the group actions, like affine spaces, similar to that. All right, so I am going to denote I is a finite set. I this is a finite set. That I will use it as an index set. And if you have trouble, then you should take I equal to 1 to n. And as you know, we are writing square matrices as M, I, K. This is a set of I cross I matrices. All right, square matrices over a field. K is a field. And this, we know the matrices and endomorphisms, they go 1 to 1, right? So this is on the other side, we have endomorphism of a K vector space V. And V has a basis, V, K vector space with basis V1 to VI. The basis is numbered by I, VI. Clear? So given an endomorphism, I have a matrix, and given a matrix, I have an endomorphism. So this is bijective. But sometimes I want to go coordinate free. Coordinate free means endomorphism, and basis is chosen when I need to calculate something appropriately, so that the corresponding matrices will have many zeros, and therefore calculation becomes faster and easier. That is the whole point in linear algebra. All right. So is that clear? Everything is clear in this setup. So any endomorphism F, we have the corresponding matrix of F with respect to this basis. Let's call this basis as V underline. That is this basis P. And how the matrix is obtained? Can somebody tell me how do you obtain a matrix from a endomorphism?
Yeah, just make it act on the VI. So V1 will give you the first column.
Yes, very good. So this matrix will have I columns and I rows, and the ith column will come from the image of F of Vi. Image of Vi. That will give you the ith column. Conversely, if you have given a matrix, I cross I matrix, I can define F of the endomorphism F from V to V by mapping Vi to the ith column. That means I will write this as sum Vj actually. I will write Vj. This is from I in I, and then Aij Vi, where this matrix is Aij. That is how the matrix is defined. And then the matrix multiplication here will correspond to the composition. That is very good. You see, it is tedious to calculate matrix multiplication, but easier to calculate the composition. That is what I will use it. Okay, one more comment. And the field for this field is not so very important. So I will make only one remark, which I don't know whether you are familiar or not, but you will tell me whether you are familiar or not. So instead of K, suppose I replace by A, where A is a commutative ring. And for me, commutative ring always with unity. And then of course the matrices make sense. MIK, MIA makes sense. These are I cross I matrices, where I is finite set with n elements. So if you want to take these and say it is MNA, so that is a ring again with the matrix multiplication and so on. What is the other side? How will I deal with this matrix ring is the following. It is endomorphisms, A endomorphisms of V, where V is an A module, and not just A module, it is a free A module, free with basis Vi. So I want to know whether everybody know what is a free module.
Yes.
And the same statement, endomorphism will give you the matrix and matrix will give you the endomorphism. Dicto, same argument. But free is very important here. This is not true for arbitrary module V. Everybody is familiar or somebody is not familiar?
Yes,
They can raise. If they want to understand, the only way to understand is raise. If nobody answers, that means I will take it for granted that you know it. Is that okay, Sonakshi?
Yes, sir. I am familiar with this
Okay,
notion.
very good. So anybody else? Arnab? Hello, Arnab.
Yes, sir. Yes, sir. I am also familiar with this.
Very good. Then my job is simpler. All right. So what am I studying here? So I want to remind you all this matrices business is started with the solution system of a linear system of equations. M equations in n unknowns, and then you have m cross n matrix, and then we perform the row operations, column operations to determine the solution space, right? And we did elementary operations on rows, elementary operations on the columns, and then we reformed these matrices so that we could easily read of the solutions. And that method was known as the Gauss elimination method. All right, so during that time, elementary operations were performed on the equations. So what were they corresponding to the matrices that I want to list, and the group will come out of that. That group is I'm interested in studying that, and the linear algebra theorem what you proved I will convert into this new language. It's not a new language, but maybe some of you have not seen this language. All right, so what is that I'm saying? Elementary operations. Operations. There are three kinds actually. And they are row as well as column. And what were the three operations? Interchanging the rows. So I will denote the row by capital R. Rith row is interchanged with Rjth row. For I and j in I. In a matrix. And or Rith row is replaced by Rith row plus scalar times Rjth row, where I and j are different and A is a scalar. A is in K. Or multiply Rith row by a non-zero constant, where A is in K and A is non-zero. This is what we did, right? You remember when you did Gauss elimination, you used this. And mostly you use for linear system, you use only row operations. Only column operations, what you use was only for making the top entry, which is known as pivot. Choosing a pivot in the top entry that was non-zero, and then we killed the below entries and went so on. All right, so what are the matrices corresponding to this? So those are called elementary matrices. So elementary matrices. This is the motivation for studying these elementary matrices. So that now, as you see now, there are a lot of notations, so I have to be carefully in choosing my notation so that they will be self-explanatory. So first of all, identity matrix I am going to denote by EI. This is the identity matrix. All places, all diagonal is 1. Another one corresponding to this operation, the first one, that is, okay, before that, I will also write capital EIJs These are the matrix units. So this is a matrix where ijth entry is 1 and all other places are 0. So this is entry is 1 and this is jth column and ith. This is 1 and everywhere else it is 0. And why these are very important? Because Eij is a basis of MIK. MIK is also vector space and this is a basis. That is clear. Because every matrix A I can write uniquely in the form of sum of the capital EHs. So the coefficients will be the ijth entry in the matrix. And A is uniquely, this is a unique expression of the matrix A in terms of these EHs. So this is a basis. And for this, nothing special about K. The same thing works for the arbitrary ring also. I will always keep noting that. Though it is not necessary that I am going to do that generality, but wherever the results are easily dicto proved it, field is not playing any role, then I will certainly note it. So this is, so therefore we have noted on the way that MIA is a free module with that basis. So a note here somewhere, you can take A to be arbitrary commutative, A commutative. All right, next. Now these elementary matrices, how they are converted. So I will write now, I will write Bij. So these I am defining it for I comma j in I and I not equal to j, and I will take any scalar A, and for that I am defining. So Bij of A, that is by definition, you take the identity matrix EI and add A times EH. And note what it is. So this is a matrix. All entries on the diagonal is 1. And I not equal to j. At ijth place I am putting A. A is somewhere here. And this one is jth column and ith. Is the definition clear? And this matrix is precisely got from the identity matrix by multiplying this j. So this jth row to the ith row. So maybe I will change that notation here, but fine. Is that clear? This matrix is obtained from the identity matrix by performing the elementary row operation. Ri is replaced by Ri plus A times Rj. So that is that elementary matrix. And we know that when you have arbitrary matrix A, now see I cannot use the letter A. So suppose I have arbitrary matrix capital A, Gothi K now, I have to use it. And if I multiply these by Bij from this side, then you know what it is, how to compute this. Similarly, pre and post. These I will not write, but does anybody know? Quickly, can somebody say what it is? This is what you do in linear algebra. Nobody knows? You have to respond. See, unless you respond, we cannot go on in this. Ishan, do you know this?
No, because I can't understand your notation. I know what Bij is, but that No. That's fine. That circle kind of thing.
Which circle?
So after Bij of A, you
That is
put
a
something
matrix
that
A.
looks like pi.
This is the matrix A. So, okay, call it matrix A. Now, do you understand?
Yeah, this is multiplication of matrices.
Yes, but what it is? How do you obtain it? What is this matrix in connection with A? How this pre-multiplication
this is
of
A
these
plus.
elementary matrices does effect on the matrix A? That is my question.
Okay, so this is just all that it is doing is this becomes A plus. You add the one moment, please.
That you are giving me a definition. You are asking me to plug it in here, and that is the answer you want to give. No, I don't want that kind of answer. I want what happens to the rows and columns of A.
Sir, in
That
the
is what I
first
want.
case, the row rith row goes to ri plus a rj.
Very good. So this is the matrix obtained from the given matrix A by replacing ith row of A by ith row and adding A times j row to that row, and other rows are
So that's
intact.
what I was saying, that you split it up. I mean, to get that this is indeed what happens, you split it up as the identity matrix plus.
I am not asking you the proof, Ishan. I wanted an answer like this. Now can you tell me this one? This one, the next one. Now I am multiplying from the other side. Matrix multiplication is not commutative. So this will happen now. What will be the result? Like Sonakshi told me in this case, what is in this case? All right, anybody can answer? So the simple, very simple principle, pre-multiplying row operations happens, pre-multiplying by elementary matrices correspond to the elementary row operation, and post-multiplying is equivalent to this column operations. Row elementary column operation. That is what this means. So that means here ith column will be replaced by ith column plus A times jth column. That is what we do in a Gauss elimination. Where, for example, when you want to find the inverse, or when you want to eliminate the variables from the linear system of equation. That is what operations we do. All right. Now what I'm going to do is I'm going to take all these elementary matrices and generate a group. So first of all, I want to note few important properties of the elementary matrices. So what are the properties that we will use often in the following? Number one, transpose of the elementary matrix is Bji A. So that is the transpose. That is again very easy to check. Second one, if I multiply two elementary matrices times B I J B, where I J are in I and I not equal to J, and A is a scalar, A, B are scalars, then this is nothing but Bij A plus B. That is very easy to check. I am not going to check. All right, here you can do it. You can just put a definition and mechanically check it. Or you understand and you check it. In particular, what happens? In particular, I want to write consequence of 2, very important consequence of 2. In particular, this matrix Bij A, this is invertible. And what is the inverse? I will write down the inverse. Bij A inverse is Bij minus A. That is the inverse. All right. So all these elementary matrices are the non-singular matrices, and this is a group we know. This is I. I should have written this is I. So therefore, elementary group is the definition. Subgroup generated by all this B, I, J, A, I, J elements in I not equal to J, and A is in A is in K. Subgroup of GLI K is called elementary group. An elementary group. And I will denote by EIK. And I want to study this elementary group. For example, when K is a field, finite field, order of this group, and so on. Group theoretic properties of this elementary group. That is one. And this group is very very important even for the research. All right. So I am collecting some other groups which arise from the matrix groups. All right. So obviously this group, these matrices also we can define by using the automorphisms. What will be the automorphism corresponding to this Bij? You can definitely write down. That means only Vi will go somewhere, right? All right. So that in the proof I will do that. I will not multiply matrices. I will compose the maps corresponding to them. All right. So another one which I want to recall. This is all recalling today. Another one what I want to recall is special linear group. That of course you know. Look at the determinant map. So determinant, think of it as a map from GLNK or GLIK to K cross. Any matrix A. I want to get back to my notation. These are Gaussian K to determinant of A. And if your matrix is non-singular, that is equivalent to saying the determinant is non-zero. So this makes sense, and this is a group homomorphism. This is a group homomorphism. That we know. That is the property of the determinant. Determinant of the product equal to product of the determinants. So that means it is a group homomorphism. If you want to do it for the ring, then you will have to, this is the correct notation, A cross, then the determinant should be a unit, then only it is invertible, otherwise no. But anyway, let us keep because you may have problems more with that, so I don't want to get into the most general situation at once. All right, so determinant is a group homomorphism. It is surjective also. This is surjective is obvious. Because given any scalar, I can always find a matrix whose determinant is that one. For example, if I have A, where do A go? Which matrix? I'll put A somewhere in the first and remaining ones, and this 0, 0, 0, this. This is the matrix whose determinant is A. It's very simple. All right. So that is, so the kernel. Whenever you have a group homomorphism, you talk about kernel and image. Here image is everybody. So the kernel of the determinant map is precisely what I call it SLI. This is a special linear. This is a special linear group. That is the definition. So therefore, I have an exact sequence 0, SLI, K, to GLIK, to K curves, to 0. And where is that the group EIK we have defined? Look here, all of these guys, so I forgot to mention that all these guys, all the determinants of Bij A, they are all 1. Because I is not equal to J. Remember this, I is not equal to J. So therefore all these Bij's, they belong to this SLIK. And therefore the subgroup generated by that will also go inside SLIK. So this EIK is actually a subgroup of SLIK and this is a subgroup of GLIK. And now suppose, and there is another group I want to consider here that you would have noticed, another group. But before I do that, now, for example, when K is a finite field, if K is a finite field, let us say with Q elements, then we know the order of this. We know order of this. Exercise sheet will tell you what is the order of this. And we know order of this also. This is Q minus 1. Therefore, we should know the order of this. All right. So we know that. Now another group which I want to consider. So the diagonal elements, diagonal matrices. So the diagonal matrices. I am going to denote by DAG, DIAG for diagonal, and A1 to AI. AI, I is varying in I. So this is same as writing AI. You see here, this is very convenient to write. And matrices will take more space also. So the diagonal, when is it invertible? Invertible, this belong to GLIK, if and only if all these AIs are non-zero. And in that case, the inverse of this is precisely DIAG AI inverse. That is the inverse. How do you multiply diagonal matrices? Just multiply the diagonal entries. All right, so these are the diagonal. And also there is one more group that you have noticed here when I wrote this. So I consider that group, I will write DK. DK is, these are special diagonal matrices. They are diag A in the first position and the remaining positions 1. So A11. And this obviously get identified with whom? This get identified with the field. And if this is invertible, then that will get identified with K cos. And why are they important? Another one is maybe all the diagonal entries same. So that is A times the identity matrix. And these matrices are also called, what are they called? I forgot the name. What are they called? Roshni, what are they called? These are the matrices like this. All the entries.
Scalar matrices.
Sorry?
The scalar matrices.
Scalar.
Yes, sir.
I don't know. There is a name to that. I forgot right now. All right. Now, why did I recall this? I want to describe. You see, all these groups are non-commutative. This group is non-commutative. I want to know what is the center. So, center of Z of GLIK. This center is precisely, I will tell you, it is, what are they called? Is it called scalar matrices? I don't know. They are precisely these matrices. A, E, I. A varies in K cross. This you would have seen. Have you seen or no?
Yes, sir.
Yes, sir.
Yes, sir.
Fine. It's enough that if I want to analyze where do they which matrices commute with these elementary matrices, that will tell you the answer. Already that is enough. So to check this, I am saying to prove this, analyze when is Bij 1, which matrices commute with this. If they commute with every matrix, every non-singular matrix, then it will commute in particular with this. And this will tell you the answer. Already this equation will tell you the answer. All right. So that is one thing. What is the center of another one? I am interested in the center of SLIK. So that will be SLIK intersection with the center of GLI. This is also obvious. And then what do I write answer? The center therefore is, I will write the answer on the other side. This is equal to all those scalar matrices such that A power n is 1. Because scalar matrices have diagonal A and they are special, therefore determinant is 1, therefore A power n should be 1. So these are precisely the roots of unity, nth roots of unity. That's how the field comes in the study, nth roots of unity. This is precisely mu of K cross, where mu of a field means this is a multiplicative group and nth roots in this that form a cyclic group. Do you know this? Is it clear what I am asking?
Yes, sir.
So this is a cyclic group that you have to prove it. This is cyclic group. Ishan, do you know this? Hello, Ishan.
Yes, I do.
Do you know this statement?
Yes, sir.
If you take a field and then take nth roots of unity in that field, that is a finite group.
Yeah, I do.
And cyclic. Do you know the proof? Hello, are you there?
Not, yes, I am not offhand. I believe it was, but no, I cannot recall right now.
So proof. So you should prove it or recall the proof.
Yes, sir.
So, All right, therefore, now I consider two new groups which will arise from GLI and SLI and their centers. So these are the definitions again. So PGLNK, PGLIK. This is GLIK modulo the center of that. Center is always a normal subgroup that we have seen. So this is called projective linear. And I want to show you that this projective linear group is precisely the analog of the affine group corresponding to the projective space. So this is a very geometric group. That is why I was asking you, do you know projective spaces? All right. So that is one. And the other one is obviously, if I do this, then I have to do it for SLI. So PSLI K, this is by definition SLIK modulo center of SLIK. This is special projective special linear group. Maybe the special word come before projective, I don't know. These are the two groups that we are going to study. So first I want to answer so what we will prove in the future, that if I don't know whether I will prove it in a detail or I will sketch the proof. I want to prove this theorem, which is very, very important theorem. This is Jordan, 1870. Say that PSLIK or YK FQ. Let me just state a very particular result. This is PSL2 FQ is a simple group. And that is the first time this Jordan, you know, Jordan is the same Jordan who you might have heard the name Jordan canonical form. The same Jordan. Same Jordan with, if you have heard the name Jordan curve theorem, the same Jordan. And these appeared in the first ever book, appeared in Galois theory, that was in 1870, written by Jordan. That is where he proved Jordan canonical form. And Jordan canonical form, he proved it for finite fields first, and for that he had to study this GL, SL, and so on, all these groups and matrices, and during the course of that time he proved Jordan canonical form. But the aim was this. Aim was produce simple groups which are not isomorphic to alternating groups, a different family of simple groups. That was his aim and understanding. And if you see, the whole proofs there and whole understanding was, or motivation was coming from Galois theory. And Galois theory means group actions. And this proof is very, very simple. And it is a tying up with the linear algebra with group actions. And it's not much. It's not difficult at all. But there are many pieces you have to join together. All right. Now, the next, so this we will prove it. In the next, I will at least try to compute what are the orders for finite fields and what are because we are interested in finite field, over finite field, these groups. And as the name suggested, they are coming from the collineations of the projective spaces, like affine collineation. They are affinities. They are affine bijective maps from affine space to affine space. Now, corresponding to affine space, there is a projective space, and these are the projective automorphisms of the projective space. And this group, how it acts, not that group, it was acting simple, transitive. Now this group is acting even more than that. It's more stringent. This will be what is called triply transitive. So all these things we will develop and do it. And I want to do it quickly. Therefore, you have to cooperate and you have to also study and ask me the difficulties if you don't have the right difficulties. All right. So now first I want to write down what is I want. So some calculation I want to do. Some examples. All right. So we have the determinant map GLNK. Now let me write it. If I has cardinality n, I will write instead of GLI GLNK. GLNK to K cross. This is a determinant. And all right. And then we know if I go, I have to now create a notation. See, you have realized when we define this group, this center of SLI particularly, that power comes. All right. So when I go mod it, what happens here? What do I have to do? That's what I want to write down. So this will induce a group homomorphism from PGLNK to K cross mod n times n on the left side K cross. I will explain what is this. So hold on this. I have to explain this notation, and this I will keep using it more often. Therefore, I will use it here. All right. So general, this is a general notation. So if you have a group G, G is a group, and so you see, and an element A or X in G. Oh, G. All right, so I have this power map. G go to G. This X is not fixed. So let me erase this. X is not fixed. N is fixed. N is an natural number, let us. And I have a map G to G. X going to X power N. This is a power map. Do I have the notation here? Okay, this is it. So then, when this is a group homomorphism. When is it a group homomorphism? When G is an abelian group, definitely, right? So G abelian. This is a group homomorphism. This map is very important because it will tell you how to find order of X and so on. And whenever you have a group homomorphism, there is a kernel and image. So the image of this, so this is this, I call it a power map. This is called a nth power map. For example, when G has order n, then this map is a trivial map. because of Lagrange's theorem. Things like that. So therefore, the image of this map, image I will denote by G, nth power element, all the powers, all the elements and their powers. That forms a subgroup. And that I am denoting by this side. I am forced to denote this side because the other side, if I write it, it has a different meaning. So this is a subgroup. This is a subgroup of all these elements, x power n, x varies in G. They are nth powers. And what is the kernel? Kernel equal to, now I will denote again, running short of notation, so I'll write it below. So this is by definition what? All those elements x in G such that x power n is identity. So these are like nth roots in G. And now I am going to apply these two. This is our group K cross. All right. Now, therefore, this now is this clear. This notation is clear now. K cross n K cross. They are the images. And now I say that the GLN mod this. See, we have defined PGLN is the GLN mod the center, and we know the center of GL. Center of GL is all these A on the diagonal. So they will correspond to the A power n. That is how we have identified with. So that is where precisely we are going mod. So they become 0. So therefore this map, so we have this composition map here. This is the natural surjective map. This is a subgroup which came out of the all powers of elements from K cross. And then this map have to induce a map here. To check that, I will have to check that the center here, center of GLNK, that goes to 0 here. So what are the centers? Elements in the center are precisely A times identity matrix. These are the elements in this center. Where do they go under determinant? They will go to A power n, and when I push it here, they become 0 here. And therefore, it will induce a map mod that. Is that clear?
Yes, sir.
All right. Therefore, now I can calculate. And what will be the kernel of this map? So this is the map I got induced from this determinant map. And I want to say now, what is the kernel here? Kernel of this map. So kernel of this map, I want to write it. So I will write kernel of this map is precisely PSLNK. So what is this map? Matrix that so A power n becomes 0 here because you go and mod that, and that is precisely the center. That is precisely the definition of PSLNK. Remember PSLNK? Definition is SL mod the center. But what was the center of SLI? They are precisely all A power n, and they are all trivial then. That is the center. So all these matrices, they further will go to 0 under this map. And precisely they will only go to 0. Therefore, kernel of this induced map is PSLNK. This is trivial. Think about it. It's not. I'm not saying a great thing, but this will help us to calculate now their orders. Let us do that before I end my lecture. So I want to calculate first K equal to FQ. I am taking K equal to FQ, finite field with Q elements. Q is definitely power of P, we know. All right, first of all, do we know? We know. I will not write down what is the order of GLNK. This we know how to compute. This is exercise set 3. I don't know the number exercise, so this is done in that. GLNFQ. Why write K here? FQ. So I will write everything in terms of this. Because that number we know what it is. So first of all, SLN. SLN FQ. Order. What is the relation with GLN and SLN? That is the kernel of this map. This order I know, this order I know, and therefore I know this order. So this order is Q minus 1. It's the non-zero elements in K, so it's Q minus 1. Therefore, order of SLN is 1 by Q minus 1 times cardinality of GLNFQ. The next, cardinality of order of PGL and FQ equal to, what is PGL and FQ? That is this. This is not the center. How many elements in the center? How many elements in the center? We know the center. This is the center, no? How many elements in the center?
Q minus 1.
Say it loudly, please. I can't hear.
So it is Q minus 1.
Q minus 1. Very good. So therefore, this cardinality is also same. 1 by Q minus 1 times cardinality of GLN FQ. See, they have the same cardinality, PGLN and SLN FQ. Next is cardinality of PSLN FQ. All right, so what is it? So here, look here, PSLN. That is same as PGLN mod the kernel of this, that is PSLN. This order I know. This order also I know. What is the order of this? What is the order of this? Nth powers. Can somebody tell me? Very simple question it is.
Q minus N.
Q minus
N.
Why N?
So nth root, like.
See, suppose if how is it done with the roots? I don't understand your argument. See, once you know the kernel of this map, then these PGLN mod SLN will have same order as this, no? Is this map subjective? So I will write down the answer. So this answer is not as easy as you think because it depends on the nth root. So D times Q minus 1 times cardinality of GLNFQ. And what is this D? D is precisely the GCD of
N and Q minus 1.
Q minus 1 and N. Very good. So I want you to check this before you come. And how will you do that? See, you have to compute the kernel of this map. That is this. And that is obviously related. The kernel also I told you, no? Obviously it is related to this nth power. And if you want to know nth power, you have to know the cardinality G and cardinality of the kernel, that is nth roots. So it is connected to both. So you have to tie up things together and come up with this proof of this formula. If you don't, I will do it. All right. And another thing is, maybe here you will need the following fact. Here, that is what I said. Here you will need the following fact. For checking this, I will write down what you will need. You will need the fact it is connected to the field only. We know FQ star, FQ cross is cyclic group of order Q minus 1. And then I said that if I take this group, roots of unity in this, so mu FQ star, what is this group? This is the group of all elements here, that is all those A in FQ cross such that A power n is 1. So that n also should come in the notation. Mu n FQ is, this is the set of all nth roots of unity in FQ. So this is a cyclic group. And what is the order of this group? That is what I am asking. What is the cardinality of mu n FQ cross? That is what you have to find out. And the answer is, it is a GCD, it's a D, which is a GCD of Q minus 1 and that n. That is more or less obvious from the definitions. All right, before I close, I will take 2 minutes and then we will close. Just to get more familiarity. Probably you know this. If you take the field K equal to C, and I take mu n C, this is also deal. Why write cross there? Mu n C, this by definition, nth roots of unity in C. All those Z in C such that Z power n is 1. This is a subgroup of C cross. Multiplicative. This C cross is a multiplicative group. So this is a multiplicative subgroup of C cross. Is it finite? Is it finite?
Yes, sir.
Why? Can you tell me one line proof?
Fundamental theorem of algebra.
That is too big. Lesser than that, I want to know the proof.
But it's the roots of unity.
So what is new thing you are telling me? I am asking why is it finite? And what is the order? What is the order of this group?
The order of this group is n.
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 Why?
This is the collection of all elements of C of I mean like roots of unity. Collection of all Z such that Z raised to n is 1.
But you are only reading the definition I wrote. Why now if I take C instead of C, what if I take R, then what is the answer?
So all elements in this group will have order less than n, and there are okay. Let me. No, I will think.
So this polynomial z to the power n minus 1 will have at most n roots.
Why don't you say exactly n root or
Exactly
C?
n roots in case of
So
complex.
that is the fundamental theorem of algebra.
That
It
is
has exactly n
fundamental
roots.
theorem is much more. Fundamental theorem says every polynomial of degree so
Polynomial
and so has so
splits.
many roots. And why so many roots? Why n element there? So Sonakshi, you are saying correct. Z power n minus 1, these roots of these polynomials in complex numbers, that is this notation. And you will have to tell me why the cardinality is equal to n, why there are exactly n roots. That also you have to check. What is the reason?
The GCD of z raised to n minus 1 and its derivative is 1.
GCD, now GCD of what? N minus 1 and what?
Z raised, that polynomial z raised to n minus 1 and its derivative is 1.
Is, you are correct,
One.
but you are not saying it very precisely. I want precise statement.
So it will not have multiple roots.
Very good. That is what I wanted. It will not have multiple roots. The roots are different. Therefore, the number of roots equal to n. So we are using two things, that this polynomial splits into linear factors over C, number one, and number two, no root is repeated. That is tested by checking that the differentiation of this polynomial and the original polynomial have no root in common. The differentiation of this is precisely n times z power n minus 1. And therefore, the only root of the derivative is 0, but 0 is not a root here. Therefore, they don't have any common root. Therefore, the number of roots are precisely n. And therefore, this group has order n. Moreover, this group is cyclic. Moreover, mu and C is cyclic. So this also needs a proof. Why is it cyclic? Ishan, do you know why
I
it's
was
cyclic?
trying to do. I was going to say that this group mu n c is generated by e to the I theta e to the I to 2 pi by n.
Yes, but why?
Yes.
Why? Where did you get that from? How did you get that from?
Yeah, I can do that. So if you write.
No, I'm not saying that
Yeah.
you cannot check. I say I want the reason. Why did you think about that?
So all the homomorphisms
If
from a finite
Because,
group.
so
if you have
the
read
nth root,
somewhere, see, if
so
you have
I
read,
can say that the nth roots of 1, I can find a complex formula for them, for the roots. And I can see that if I multiply by using De Moivre's formula, that when I multiply these two things, they will add up to give. So can I tell you how the roots
no,
look?
I don't want that. But suppose I replace C by R or Q, is it still true? I want to replace this C by arbitrary field, in fact. Mu n K. And K is arbitrary field. Then the two main questions I want to ask. What is the order? And is it cyclic? These two main questions. And had you known the proof of this fact in an appropriate way, you will imitate it. Because what is more important, it is a field. And it is related to the polynomials and zeros of polynomials, as you saw. All right, so think about this. I want to answer next time. And all of you know this, but you are not tying with each other. That is the question. All right, so already my time is.
is the reason is that the multiplicative group of the field K star is cyclic, and so it will have a generator
That is
that
not
will
true.
give.
That is not true. Multiplicative group of a field is not cyclic in general. C cross is not cyclic. R
For
cross is
finite
not
field.
cyclic.
For finite field.
But I want to ask this question for arbitrary field. For finite field, yes, but that also needs a proof. Why multiplicative group of a finite field is cyclic? That also needs a proof. Okay, even if you grant that, how do you compute the order of mu and k in that? Mu and fp, what is the order? That is what our question was. See, mu and fq, what is the order? And I said this is the order. And how do you calculate this?
For the finite field, I have half a proof. It requires something from groups which I can prove, but I need a bit of time. Which is if you have that for every, so this for the finite field, let's take the order is q, right? So
Yes.
you're taking f cubed, and
Yes.
yeah, and it's forming a group. And what happens is if you take something which divides q, let's call it n.
There is no q. There is no order. Is not q. Order of the multiplicative group is q minus 1.
Yes, sorry. Yes, of course. If I take n dividing q minus 1,
Yes.
and I look at the solutions to that, okay, solutions to x to the n is the identity, then there are going to be less than equal to n solutions.
That is trivial. That is always that you don't need
Yes. I know. I'm just saying that. And a group where this happens, where for every divisor of the order, the roots of x to the divisor equals 1. If that is at most the divisor, then such a group is cyclic.
Ishan, it is too complicated to think for me. Answer is much more simpler if you think.
So can I say something?
Yes, please.
So this is Parnashri. So this finite group thinks that the group of units is forming a cyclic group. I'm going to discuss it in today's tutorial. So I will ask Ishan to present his thoughts in tomorrow's tutorial.
Fine. Okay. So I will send you the PDF file of this, and now you have the tutorial, is it?
No, sir, I don't have tutorial. I think it is other tutorial.
Okay, so you will discuss it tomorrow.
Yeah, I will discuss it tomorrow.
Fine. I will send you this lecture PDF file, and then I will stop.
Sir, may I ask something?
Yes.
Yeah, no. So do you want me to submit a write-up of this proof for the tutorial?
No, I don't want you to submit. You can write it up, but I don't want you to submit.
I don't want to read any proof submitted. I want to see oral arguments. Okay, I'm sending